Well, you'll see. I think from something very easy to comprehend to something not very straightforward, but they are all considered very, concept called greedy. And, okay, and do you have any connection to the other end? Well, I don't know. Okay, so I guess we can get started. And I do need one volunteer for the recitation of tonight's notes, even though I think I will provide the source file for this presentation slides, but there will be some essential missing components and maybe some relevant references that I think for someone who's willing to help with the discussion with other students, maybe I think the volunteer will also get a small trophy for doing that. Any volunteer at all?
No, no.
Well, I mean, don't be. Well, I just hope that the volunteer turned student can at least keep track of all the detailed talks of the, and that's very important. So take that as an opportunity for you to at least have some initiative to dig further into the subject, and especially for those who really are keen into the algorithm part of the design. I would say the lecture is interesting because it's hard to find from the standard textbook. And also this is basically based on some talk that I've done in the group seminar that I think some of you already seen this before, but probably can have a better understanding on certain subtle issues if you want to give a try. Okay, thanks, Gang Liu will do this. And
same thing like
well, to your best extent, try to basically convey this idea as your recitation notes, fill in some of your own understanding by transition from like just high-level description of this to some detailed description on some specific subjects. So, of course, I'm going to start with what is a greedy algorithm? What are the essential components when you try to design some algorithm that solve practical engineering optimization problem? And some may be discrete in nature, some may be discrete and continuous optimization problem. I'm going to talk about some typical examples you'll see and some not so typical examples which are related to my own research, including some combinatorial optimization that you may want to get a better feeling on this through some interesting applications. And then basically I will try my best to provide a unified viewpoint on, for instance, when do you expect greedy algorithm to work and how to justify that the greedy algorithm can guarantee you to have close to optimal performance? And what are some essential thinkings behind it to drive you along this line of thinking? And also, at the very end, I also want to mention that there are some other techniques available. Whenever you have a complicated optimization problem at hand, in general, this is just one way of thinking, and we also covered some other useful techniques. I want to maybe provide a bigger picture in the summary part. Like last time, Mr. Gang Liu asked me about my take on what would be the essential components in engineer optimization that when you finish this semester, you got to know, and maybe even to probe further when you get to your own research problem. So that's my hope. And also, I have to apologize first if this lecture lasts a little bit unusually long, especially like the lecture before your spring break. Just bear in mind, some part of this narrative will be exciting that I hope maybe even the recitation notes taken by Gang Liu will also motivate some interesting discussions, which I will post on Blackboard, and let's use that as also another arena for you to put some of your own input and maybe your own problem for term project or some other things you want to do so that we can basically get some interactions after this. So what is a greedy algorithm? And in fact, there's no generic definition for that. And if you look at Wikipedia, which I actually chose literally to copy some essential components to it, a greedy algorithm, you can say, is any algorithm that follows problem-solving meta-heuristic of making local optimal choice at each stage with the hope of finding the global optimal. OK, so you can see that in general, you have a bigger problem. You decompose that into different stages. But each stage, you try to make your best choice only with this local objective function. And by doing that repeatedly, there's a hope that you can get to the global optimal. But in general, you cannot guarantee that will happen. And of course, the key structure you will see is that the problem can be decomposed into countably many stages. And then your greedy choice depends only on the choice that you made so far, not on your future choices. Meaning that once you made a choice, there's no turning back. And that's different from other techniques like dynamic programming or some other sub-modular function minimizations that we mentioned before. And this is actually extremely simple when you try to implement a greedy algorithm. Usually, it's just maybe a few lines of code that can do that, that can solve the problem. But of course, the difficult part is how to justify that your greedy approach works for some most sophisticated optimization problem. And of course, I will try to provide my take on how we can justify the greedy algorithm either as very good that gave you the optimal solution or maybe near optimal solution with quantifiable performance gap. And of course, we need to understand about the structure of the problem in order to make such a claim. So let's think about what are the typical applications where you can study the greedy algorithm. I think Gordon just mentioned that he learned from computer science undergraduate curriculum in algorithm design, right, about the greedy algorithm, and which I think he will be pretty much familiar with some interesting combinatorial problems where greedy algorithm actually works, like the Prim's algorithm finding the minimum spanning tree and Dijkstra's algorithm finding single source shortest paths, and also some geographic routing problem in ad hoc network, like maybe internet, so-called distance vector routing protocol, and some other things related to wireless sensor network. And also you can think about like a local or taboo search for solving traveling salesman problem is some specific version of using greedy heuristics. But these are typical things. I will try to mention a few examples later, probably very soon. But in addition to that, we also see some other engineering problems where at the surface level, you don't see greedy algorithm can play any role. But in effect, it does, especially in so-called sparse representation problem. I think Lippy probably is very interested in that because of her own research is related to this. So I'm going to mention some problem related to how to maybe find good basis to represent your signal, and also how to apply some efficient algorithms such as basis pursuit or orthogonal matching pursuit to solve this kind of subset selection problem, including some regularized least squares or LP regularized optimization problem. Yes?
So Dijkstra's algorithm would be the exception to the norm, or the greedy algorithm actually gives you the optimal solution?
Well, these are very interesting cases where you can see that either greedy algorithm does provide you the optimal solution, or maybe sometimes you can prove that under some restrictive assumptions, it can provide you close to optimal solution. Like in this Dijkstra's case, it is, because that's why it has a name called the Dijkstra's algorithm. And also, I'm trying to provide some other non-standard problem, like Markov decision problem, which is very typical in reinforcement learning. And also, I will try to introduce some important concept. I think for computer science major students, probably you've seen this before, which is considered randomized algorithm, and sometimes use random technique to make your algorithm efficient, and sometimes use de-randomization to even reduce the requirement of using random number or pseudo-random number generation. And also, I'm going to talk a little bit about the connection to some real engineer application like compressive sensing. That's the research work that I'm currently very interested in. And also, I hope that based on this, I will try to provide my view on how the greedy algorithm can be applied to various engineer applications. In addition, I will try to interpret the greedy algorithm as somehow like a coordinated descent algorithm, which in each step you try to go like along each coordinate system to go descent, reduce the objective function, so that we can gain some insights on when or how the greedy algorithm works and how to construct good greedy search directions in some engineering problems. And also, I will try to use probabilistic approach to justify the optimality of certain approximation algorithm. And the example is called combinatorial discrepancy. And that's a very interesting optimization problem to talk about. And if time allows, I will try to also build some connection with some other engineering problems that you can see maybe from some relevant research topic that may drive you toward maybe your own research that hopefully will provide you some, at least one arsenal for you to tackle some complicated combinatorial problem. Okay, so what is a greedy algorithm? And without getting into some detailed construct, let's look at one simple example. Suppose that you count certain amount of money using the fewest possible bills and coins. Let's assume that we are trying to break down $6.39. And in general, what a greedy algorithm does is just at each step, take the largest possible bill or coin that does not overshoot. So what would you do? Let's take this example, $6.39. What do you do if you create a greedy algorithm? Okay, so you don't want to overshoot. The largest bill, the first one you choose is what? $5. And then what? And then you have 139, so you choose $1, and then you have 39 cents. What do? You choose 1/4. Okay, and then a dime, and then what? Okay, and that's it. Okay, and is that optimal? Yeah, or coins. Yeah. It is in this case. Oh, okay, I see. Like Leafy is very cautious about the claim. Yes, I'm asking about this case, and how do you know it is optimal? Well, if you ask this way, then I will just slightly change the example a little bit. Okay, so let's say we have some fictional monetary system where we can have these currents, like 1 current, 7 current, and 10 current coins. And counting this, we have 15 currents, and you want to apply a greedy algorithm. What do? Because our monetary system is what? 1, 7, and 10. You don't want to overshoot, so you put what? 1 10 current coin, right? And what you will be left is what? 5 currents. So what do? Put another 5 1 currents. Okay, so overall you need what? 6 coins. And if you don't do greedy solution, well, what can you do? In fact, you can choose what? 2 7 currents, and then end up with what? Only 3 coins. You can do that. So what can you say about this? The greedy algorithm cannot provide you the optimal solution to this monetary system. Okay, so what's the difference between the previous one and this one? Yes?
In the previous example, all of coins, there are multiples of each other, or you can find it.
Well, can you say like a quarter is a multiple of a dime, or?
Oh, well, at least they share a common factors.
Well, here I believe they all share a common factor of 1 current.
Well, I mean, higher than 1. I mean, they share a factor. I don't know. It doesn't work like that.
If you sort these like units,
okay,
then any one unit has to be less than half of the next one in value.
Does it?
In the US one.
Okay. And is that the necessary condition for the greedy algorithm to be optimal?
When you're counting money, it might be, sure. I don't know about in general. I feel like, yeah,
I think it is sufficient, but is it necessary? That's.
I don't know the answer, honestly. I know, for this problem.
Okay.
What would be necessary is not sufficient here.
I guess one interesting question that I left for the recitation note taker to answer is what are the necessary and sufficient conditions for the greedy algorithm to work for counting money? What type of monetary system would give you the next property that ensures greedy algorithm to work? So now you can see that the greedy algorithm is extremely simple, right? However, it may or may not work. Purely depends on the structure of the problem. Is that clear? Okay, so another example. Minimum spanning tree. Well, if you think about a graph where you have a collection of nodes and then some edges connecting these nodes, and then the problem is how can you find the subset of the edges of a graph with the least cost that connects all the nodes? Okay, is that clear or not really? Okay, so maybe let me draw something from the document camera. Okay, and I'm having some difficulty in getting the document camera on local. You mean the this light? Okay, yeah, let me see. Maybe that's right. But that's not good enough, I guess. And also, there's not enough light from here. Okay, thanks. And we can say there are some connections of this graph. Okay, so there are some edges connecting these nodes. Okay, and then of course each edge may be associated with some cost. Okay, so let's say this is 1, 3, for instance, 3, 5, 6, and 7, 8, 6, 5, 9. Okay, and then minimum spanning tree means what? Of course, you build a tree that connect all the nodes, right? And then you want to minimize what? The total cost of those edges. Okay, is that clear? So in general, how do you solve this problem? you can say, I want to enumerate all the possible spanning trees and then find the minimum. That's not efficient, right? And then, of course, we want to say how our algorithm can be significantly faster than doing this exhaustive search, right? Finding the minimum spanning tree. Okay, so since I'm talking about a greedy algorithm, what do you do? You randomly select one node? Okay, okay. Okay, so you randomly select, let's say you select this node. And then you, okay, so you select this node, and then you connect this, okay. Okay. Let's say now which one, you select this one. And then which edge you are going to connect? One of this, okay, so let me use this. Okay, and what's next? Okay, so now you try to find where to go, the minimum, right, which is this, okay? And then what? And then any of this, the minimum would be, for this node, you select any of these 6. Okay, so I select this one. And then what? Finally, you consider this node, and then you get to this. How do you know each step is greedy? Because you only consider the local connections to that node, and then what? You find the minimum edge, okay? And that's how you get to the minimum spanning tree. And how do you know the algorithm will stop? Because eventually, you will cover all the nodes by spanning this tree, and you don't want to have any cycle from these selected edges, right? And then finally, how do you know this solution is minimum spanning tree? I think you understand about the algorithm. You can start by picking any node and adding it to the tree, and then you repeat by pick any least cost edge from a node in this tree to a node not in this tree, and then add the edge to the new node. Stop when all the nodes have been added to this tree. And this is a clearly greedy algorithm, right? And why it provides you the minimum spanning tree? It's and the idea is based on so-called proof by contradiction. Because, of course, each step is greedy. And if you say, well, if there's another tree that's not included by this procedure, then what will happen? At some stage, because the node has to be swept, meaning that you can now add that edge to this tree, you should get to the other tree, which doesn't happen. So this algorithm guarantees to provide you the minimum spanning tree, one of these minimum spanning tree in that particular example, right? Because whenever you have the same class, you have to pick one. Okay. And if we try to say, okay, so now greedy algorithm can provide optimal solution to some optimization problem. What about the traveling salesman problem? I think now we all know this problem, right? But the question is, how can we basically apply greedy algorithm? Well, that's actually relatively easy. If you think about, for instance, traveling across those state capitals in the US, we say start from Baton Rouge and do what? Greedy means what? I just pick the nearest state capital that I want to visit, that I have not been visited, and I visit that, right? Once I've been there, once I reach there, then what? Pick the next one, like what we did in minimum spanning tree, and then basically we find a solution very efficiently for the traveling salesman problem. But will that provide you the optimal solution? Why not? Okay, but in fact, if you say you will not, then just provide one counterexample would be good enough. Can you?
In the previous example, you were allowed to start from any of the nodes that had already been used, but in this one, the salesman's going to be backtracking a lot.
Yeah. So for this example, for traveling salesman problem, greedy can be somehow not as effective as doing this. And the reason is mainly that if you think about, let's say Baton Rouge is here, okay? And then the nearest neighbor is here, then definitely I will go here, right? And later what will happen is that from there, maybe I have nowhere to go. For instance, maybe I have another neighbor here, another neighbor relatively here, right? Once I reach here, then what? I will have to go here because every step is greedy. But sometimes, maybe if I sacrifice a little bit, let's say I have another major city maybe here, then the first step, if I sacrifice a little bit to travel to this city, then what will happen is later it will be nice to go here and then maybe here. And then let's say maybe I have another adjacent city here. And then I can go here and finally reaching that state. Is that clear? Oh, not really. Well, I'm saying that if you have one counterexample that greedy doesn't really provide you the best tour for the traveling salesman problem, then of course it doesn't work. You cannot guarantee greedy algorithm that provides you the optimal solution, right? So the first step can be very wrong if you manipulate this location of the city a little bit. And we see that this doesn't work on traveling salesman problem. And Sarah just mentioned this traveling salesman problem is NP-complete problem. So what? So you don't expect like a greedy type of efficient algorithm can get to the optimal solution. In fact, we don't believe any efficient polynomial time algorithm can give you the optimal solution. Unless what? Unless P is equivalent to NP, and that's probably very unlikely based on our knowledge. Of course, if anyone can prove that either this is true or this is not true, then what? Then not only you can get instantaneous fame in this computer science or mathematics field, but also you can claim for the Clay Foundation of $1 million on this notoriously hard problem. Okay, so if we think about how to find the shortest path, I think we use this example for dynamic programming, right? And now we just look back to the same problem. Given a graph, how can you find the shortest path from one given node to not just another node, but maybe let's say all the other destinations? How to do that? Well, think about the greedy algorithm, which means what? Starting from anywhere, I just try to find where's my shortest next stop in the city. So you can say, initially, I can mark any given node as null, which means the path length is 0. And then for each out edge, I just set the distance in each neighboring node equal to the cost going to that the cost of the out edge, which is the distance from that city that I know to another adjacent city, and then set the predecessor to the initially given node, meaning that I can build the shortest path in any local neighborhood, and then what? Just propagate, right? Broadcast. And repeat this until what? Everyone knows. And in fact, this can be implemented in a distributed fashion. meaning what? No matter who announces first, eventually they will all get to the same answer. And this is like a simplified version of the so-called Dijkstra's algorithm for finding the shortest parse of a graph. So that's the algorithm. Does it work? Yes.
As long as you don't have any negative edges, it will work.
Very good. If you don't have any negative edge, it should work. Why? Intuitively, how to argue that? Still, I think it's based on like a proof by contradiction, right? For any particular shortest parse you found, it's based on what? Locally being greedy. But if you think there's a parse that being locally greedy is not really the best, then that violates the assumption we have the shortest parse for every stage. And of course, you can interpret from a different angle in dynamic programming formulation, where you have intermediate state. You can say any state is based on the distance you travel from an initial city up to this city so far, and that's optimal, right? And then what? And then you pick the shortest one and claim that's the optimal to the next city. And each stage is optimal. The difference is that the dynamic programming doesn't really explore all the possible shortest parses. It interests only what? From city A to city B. Like in the example we say, you travel from New York City to Los Angeles. You don't care about the shortest parse to Detroit, the shortest parse to what? Maybe Seattle or some other cities. You only care about from one source to the destination. But in this algorithm, in fact, it provides you what? All the shortest parses between any pair of the cities if you run this. Can you see that? Okay, and that's nice, right? So this Dijkstra's algorithm is greedy in the sense that each node only examines its neighbors for the best cost. And this is much more efficient than exhaustively search all the feasible parses. When it converges, then you can see that if you have n nodes and the average out degree of a node, meaning that from one city you can go to k neighbors on average, then the complexity of Dijkstra's algorithm is at the order of kn log n. And Mr. Liu probably needs to explain in the notes why that's the case. Anyone knows this big O notation and explain a little bit what it means? Yes?
It is an upper bound on the complexity of the algorithm.
Okay, which means what?
It means that the complexity is less than equal to.
Okay, very good. And the implication is that the complexity in the worst case is on this order. And also is, how should I say, is no greater than this order, meaning that sometimes maybe my estimate is pessimistic, meaning that maybe a few days later, Lippi found out that the order should be k log n squared, for instance. And that's less than this. That means, okay, so Dijkstra's algorithm can run faster asymptotically than this bound, and still it's considered efficient, right? So this basically just gives you some idea in the worst case what will happen. And this is polynomial complexity in terms of n and k. Is there any connection to dynamic programming? Well, for shortest parse problem, now we see that we provide the optimal solution using Dijkstra's algorithm, right? And we can also solve the problem using dynamic programming. And
Several dynamic programs happening at once.
well, slightly different. I think the fundamental difference is that there are different ways to see the problem. One is called successive approximation. The other is like doing fixed point algorithm. For instance, if you think about the gradient descent, meaning that every step you go downward, right? And eventually, for instance, a fixed point algorithm means what? Eventually, it will get to some stationary point where you iterate many times. And successive approximation is based on what? Each step, you try to locally approximate something. If you think about the difference between like steepest descent method, gradient descent, and Newton's method is not greedy at all, right? It means every step you successively approximate the objective function locally by a quadratic function. And as an analogy, here you can see that dynamic programming is not greedy at all. It tries to maintain what? The optimal stage in every single update. For instance, the state space is limited, then dynamic programming is efficient. On the other hand, if the state space grows exponentially, then what? You can still apply dynamic programming, but the computational requirement will be high. And of course, the goal for dynamic programming is to provide you the optimal solution if you formulate right. On the other hand, the greedy algorithm, there's no hope unless you prove that every stage, well, you maintain some optimality property. Okay, so you see the difference? And that's important because what? For more complicated problem, we really don't know if greedy method works or it doesn't work. So we have to look into a particular problem and try to understand it better. So let's look at a particular type of problem called the Markov decision problem. And this is very useful in reinforcement learning. And I think some of you may be unfamiliar with all these terms. And let me try to use an example. If you try to learn something, of course, there are different ways to learn. Like if you train a computer, you can say, OK, I gave you an image. OK, that's a portrait of a male student. That's a portrait of a female student. I keep doing that. Then what? Eventually, I put another testing image and let the computer to tell me is it a male or female, right? And for instance, maybe I use a fingerprinting system and then ask Mr. Yu Liu to say, OK, so put your finger on this computer and record that, and then ask Resting to do the same thing. I eventually maybe put this fingerprint recognition system on the doorway and then ask the computer to write an algorithm to recognize if it is from Mr. Yu Liu or Resting or maybe some unknown user, right? And the only authorized user can enter. And that's basically ask the computer to build some learning algorithm to do some pattern recognition applications. And in some other cases, we don't have explicit training samples. Like for instance, when you play chess, you move and your opponent move. Is this move good? After many steps, maybe you will know, right? But at this stage, you don't know. And sometimes you may say, well, this is some extreme. And what about, for instance, when you plan, like what are you going to do during the spring break? And if you say, well, I want to take some break, right? Or maybe I want to do my research, which is very unlikely, okay? And you want to spend some time, catch up the optimization homework assignment or computer assignment or the term project, which is very rare, I think, for most of you. But these are the plans. But what are the consequences? Do you know? Only at the very end of the semester, maybe you know. Maybe after your graduation, later, maybe you'll recall what you did during the optimization class. Yes, maybe suffered or hated the instructor for some time. And anyway, so that's the learning process. You can see that sometimes you get some reward and penalty in each stage, but you keep repeating doing that. And then later you'll see what's going on. And a Markov decision process describes some control problem where an agent evolves in certain environment and aims to optimize certain long-term reward. And in general, you may put some mathematical abstraction on this. You'll say, well, we need to describe about the environment, which is this capital S, the state space. And we need to describe about the agent, which is this set A, that's the action space. And also we need to describe about what? How the environment changed, right? Which is like some transition probability from this state space from one time to the next time. And also we need to describe about given a particular state, given you take a particular action, what consequence you have, what kind of reward you will get. Okay, so at any time t, if a particular state S belongs to S, and then if you take some action, which is what we call the policy of the agent, that will result in certain reward R of t. And of course, overall, you want to say what would be the best policy, which maximizes the total, maybe discounted reward, because you want at the very end you have large reward. In the intermediate stage, probably it doesn't really matter. For instance, if you say, if at the very end I get A out of 65, 70, doesn't really matter I fail in certain homework assignment or computer assignment. Okay, and that's optimization problem you have, which can be formalized by some mathematical expression about so-called value function. That's like the total expected reward associated with a particular policy. So policy is what? It's the action you're going to take, right? And this action has to be described in such a way that for a particular state, you know what to do. For another particular state, you know what to do. For instance, if you say, if Dr. Chen didn't show up tonight, I will go home. If he shows up, then I will stay. And that's the complete description of the policy. And here, I'm using this as an analogy for the state space. And then, of course, there's a transition between the state from this time to next time. In this particular example, I'm saying that, for instance, what's the probability that I will be here for this week, and how would that affect I'm going to show up next week? Okay, so you have this state transition from S to S prime, and then you have the action that associated with your policy. Then you can compute what? Your reward. And of course, this can be decomposed into different stages. You'll say, well, now I have some reward associated with at time t. If the state is S, my action is A, I have reward R of t. And then what's the previous stage? That's discounted by gamma. And that stage, at that stage, well, my state is S, and then maybe next stage it will transition to S prime. And then, of course, I need to count all the possible transitions from S to S prime and calculate the associated action with that policy and what the value would be for that particular state. Okay, so based on that, of course, now the optimization problem can be rewritten in terms of finding the best policy with respect to what? The reward for a particular state at time t, and also the transition from the previous time. And then that's the best thing you can do at time t, right? At time t, you have the reward. That's when the state is S, you take action A. Of course, if the previous state is S prime and then you transition to S, then that's a different setting that you need to consider about the value of that function associated with your reward. And overall, you may say, on average, am I doing the best? So that's basically the problem you need to answer for so-called the Markov decision process. Is that clear? Well, R is the reward, and gamma is just some discount factor. For instance, you may say, well, I did very well in last week's homework assignment, but probably it doesn't really count too much. I care more about this week's performance. At every stage until the very end. And of course, if you say they are equally important, then gamma equals to 1. You can put gamma equals to 0. That's the extreme case. That means I only count the current time. Okay? And I think that's probably the most significant math involved in describing the problem that I'm going to talk about tonight. Later will be less mathematical equations, but more thinking, thought-provoking questions regarding how the greedy algorithm plays a role in this type of setting. Okay, so now let's first don't think about how to be greedy. Think about just how to be optimal in this long-term plan. Of course, one thing that comes into your mind should be what? This is a multi-stage optimization. You consider many different stages, and you can decompose that into each stage. So one natural choice to think about optimization is what? Dynamic programming, very good. So how can we solve this problem by dynamic programming? In general, this policy should be good at the very end. So in fact, we don't go forward. We go what? Backward. We say, okay, so I consider the final time is capital T, and then I consider the state from the final time and set this initial value function to be 0. Now I do some recursion on the state so that I say at the final time, assuming that's my best policy, then what would be the best policy in the previous state? And that depends on the backward calculation of the reward function plus the transition of the state, right? And then for each stage, you record all these actions and the associated value function, and then what? And then you draw some diagram. Eventually, when it reaches to the initial stage, now you can go backwards, pick a particular transition path from your dynamic programming trellis, and then you find the optimal solution. So the complexity depends on what? The size of your action space. How many actions are you going to take, right? And also depends on what? The size of the state space for ys squared. Because remember, state has transition. The transition means, let's say if I have 2 possible outcomes, the transition will be the multiplication of this, because I can transition from 1 to 1, 1 to 2, 2 to 1, and 2 to 2, right? So the overall complexity depends on what? Number of actions, number of state, and also what? Number of stages you make this dynamic programming. So that's the complexity. Okay, and that's better than doing what? Exhaustive search, for sure. But is that good enough? Well, it depends on the application, right? For instance, maybe you have huge application, you have huge action space to explore, or maybe you have huge state space to explore. And in those cases, this order doesn't really tell you too much. And it may be bad. So what can we do? Of course, we can design some approximate algorithm which cannot guarantee you to get to global optimal, but can give you some reasonable performance. And the performance you don't know. For instance, you'll say, I run simulated annealing. On this one, you can. But the problem is, usually you don't know how well it will perform. And there are different ways to look at this problem. One is called the value iteration, which you can say is actually act like a fixed point algorithm. Essentially, you design some iterative procedure that converge to a fixed point. And here you can think about this is like an operator L to some value function V, and it works for reward maximization over infinite horizon, or maybe you can say per sample average, meaning that in the long run, doing value iteration would be good. And that's very important for so-called partially observable Markov decision process. And anyone heard about this before? No? Because now I think maybe even in computer science, artificial intelligence course probably doesn't cover this. This used to be a very important technique to address some mission planning problem, even in robotics or some other manufacturing processes. But basically, value iteration is considered a significant breakthrough to solve large-scale, partially observable Markov decision problem. And another technique is called the policy iteration, which you can say start from some policy. And this policy means what? In layman's terms, it's just what action you're going to take, right? And that means, for instance, the action it describes if the environment is A, I will do B. If the environment is A prime, I will do B prime. It's something like that. It's something actionable so that you can calculate on average how much reward I get. And this policy, you start with some good guess and try to make improvement in the iterations. Of course, how do you know you will make an improvement? You can simulate, right? You can simulate this system by Monte Carlo runs. And then, of course, this will be similar to what last time I talked about stochastic gradient type of algorithm, where you basically try to compute stochastic gradient direction and make it improvement upon the stochastic gradient. Basically, the key question you should ask is, under what condition this iterative approach will guarantee to improve, and whether it will converge to the optimal value or policy. That's the most important thing you should ask. Okay, now that's really a difficult question to answer. If you think about how should I do to maybe construct a greedy algorithm that acts like policy iteration or value iteration. To construct a greedy algorithm is not hard. You can say greedy algorithm, what it does is just try to predict what's going to happen in the state. And then you take the best action corresponding to that state, right? Meaning that you predict that Dr. Chen will not show up next week. So what's your best action? Maybe show up anyway. Okay. That's a good answer. Okay. So now you see how you do to design greedy algorithm. And then what's the consequence of that? If your prediction is not right, then you can suffer miserably, right? Sometimes you'll say, well, I need to destroy the enemy object at that location. And then I predict next time should be at that location, so I make some engagement. On the other hand, if I miss, then there are some serious consequences. And here it's very similar. If you think about each step, you do the prediction, and then you just say, I take the best action in terms of maximizing my average reward, assuming my prediction is right. And interestingly, you can say, well, that's not good, so what do I do? I should have some combination between what? Using greedy step and what? Not so greedy. And what do I mean by not so greedy? You can say, well, in other case, I don't really know what to do. Because if I should optimize something, but it's unclear which part I should optimize, well, that's easy. You can say, well, I flip a coin and just randomly pick an action, no matter what. Okay, and sometimes that happens to be good, then I should record that, right? Okay, so think about if this is really a Markov decision process for stationary Markov chain, then each state action pair will be visited infinitely many times. So I hope that that's clear even to some of you who didn't take probability class. A Markov chain, you can say, well, for each state, if you think about the chain goes long enough, every state will have non-zero probability being visited, right? And how many times? Well, if this chain is infinitely many long, then of course each state should have its equal share. Is that clear? Not equal share, I mean should have close to infinite many times being visited. And why that's important? Because you can say, well, even I throw a random coin, eventually if this state happens to be good, then I will learn something regarding my action, like how often this state will show up. And then eventually I may be okay to do a prediction. So what does this algorithm do? This greedy algorithm just say, every step, with some probability, I will be greedy. And with some other probability, I just randomly pick an action. And then just try to keep doing the balancing that. And interestingly, if you think about each step, you want to, at the very beginning, you don't want to be very greedy, right? At the very end, you want to be kind of very greedy. And if you say, I choose this to be 1 over n, the balance between being greedy or not greedy, this is being not greedy. It's 1 over n, and being greedy is 1 minus 1 over n, which is, at the very end, it's very close to always being greedy. And that works because this greedy algorithm actually converged to the best policy with probability 1. You may ask me why. Okay, so this is close to what we talked about last lecture about what? The convergence property of what? Stochastic gradient algorithm. You'll see that this step size is not chosen arbitrarily. You can see that the sum of this is what? Is infinity, but the sum of the square of this is finite. So that's important to ensure this probability, the convergence in the probabilistic sense. Can we do better? That's a very interesting question to ask. And in fact, I don't know. And that's like an open research problem. If you have some interesting thoughts, please let me know. And of course, we can collaborate if we can find out. And that's an important research problem. But we can see there's an exploration and exploitation dilemma here. That I think I emphasized quite a few times. The difficulty lies in what? We need to see enough samples to eliminate the effect of prediction error due to rare state transition, meaning that if the state you don't see very often, then what? You don't know what's going to happen. And then your prediction on that would be far off. But then if you explore too much, then what? It will affect how fast you can take the best action according to the prediction model. Okay? So in order to build a good prediction model, you need to wait. You need to be patient. On the other hand, what? If you try to be too patient, then of course your prediction cannot be very accurate compared with the best prediction model you're going to learn. And maybe let me use another analogy here. Sometimes you'll say, well, maybe we have already found the optimal policy. But what? But the greedy algorithm can never be sure in the early stage. And what does that mean? Well, for instance, if you say, I ran simulated annealing, I'm very lucky in 1 minute, I get this solution, and then I run another 2 months. There's no improvement, right? And then, but can I stop running maybe just at this particular time and say, okay, that's the optimal solution? No, because this simulated annealing, you have to explore. I'm sorry? Well, close to all of the feasible sets, right? If you say, okay, I'm lucky I get to that point in the early stage, but still you don't know that's global optimal. And here, I think the same situation about this exploration and exploitation dilemma. Okay, so let's take a short break, and then we are going to continue with another interesting combinatorial problem. Well, analytically, I mean. It is not, but still.
So if it's not a convex problem, how to analytically show
Like what you wrote, if there's only one stationary point satisfying this Cohen-Tucker condition, then what can you conclude?
So you mean give that only one solution? You mean just put the KKT condition there?
Yeah.
Okay, then that's fine.
Yeah. But basically, you already get to that conclusion, but I want to make sure you understand the consequence.
Okay. So that's fine. I think you think there's another way of saying, can analytically show this is
Well, I didn't ask you to show anything beyond the, like just stating the simple fact for this problem. Okay? Oh, yeah. And also, I misunderstood about the global how should I put it? Global convergence. Because I looked into maybe 3 optimization textbooks and some monograph, including one operations research monograph. Couldn't find any formal definition for that.
I think many situations convergence means global convergence.
I mean, I still feel uncomfortable for that wording. Well, convergence means global convergence. That's not accurate. Convergence, I mean, a sequence can converge to some point. That's clear, right? And then you'll say maybe a collection of sequences can converge to different things. That's also okay. But global convergence, you can have stable, for instance, you have locally stable, globally stable. But convergence, it's hard to say.
A sequence is a convergence, then what do you mean by
Because your algorithm provide a sequence, right? So that's why I don't understand, for instance, why we need a global convergence concept. That depends on your algorithm, right? And if you tell me, okay, I can generate a converging sequence, so what? If that doesn't solve the problem. Okay, but I would still hope you can send me the electronic version of the report and the source code for this. Thanks.
they said global convergence? Probably mean if you start from anywhere, then your algorithm will converge.
Well, it's your algorithm. That's what I'm saying. There should be some performance metric to be algorithm independent. Do you agree? For instance, if I say your algorithm converges to a local stationary point, fine. But if you say my algorithm converges, so what? If basically it just says my algorithm can generate a converging sequence. So
It may converge to anywhere.
and that doesn't make any sense to me. And if you say my algorithm can generate a converging sequence, no matter where you start, always get to a single point. So what? I mean, doesn't affect my judgment on how well your algorithm performs. So that doesn't make much sense to me. Well, that's hard, meaning that if you have a problem, you can always come up with some greedy approach, but the later stage is hard, showing that the greedy algorithm can provide a near optimal solution. That stage is hard.
But there should be some sufficient or necessary conditions.
Yeah, of course. But what I'm saying is sometimes if you say originally the problem is NP hard, then there's no hope you can get to the optimal solution. But still, amazingly, some problem does provide the greedy near optimal solution. Meaning that sometimes you can say with high probability, I can get to the optimal solution. And that's already very amazing, right? Something like you can say I run some random trials. It's very likely, just repeat for a few times, I can get to the optimal solution. But still, the original problem is NP hard.
Yeah, that's another way to find a. But that kind of method doesn't guarantee.
No, and also there's no systematic way to show even there exists such a procedure to check whether you can verify that or not. Because that procedure is, for general problem, is considered p-space complete. I mean, in computer science, did you learn like NP complete and p-space complete and some other?
Some basic like the definitions and some
Yeah.
examples. But
Okay.
they didn't detail because that goes doesn't cover.
Okay, but you do know the difference between like a p NP and co-NP and p-space.
NP and NP and NP complete.
Complementary NP, you don't cover. Okay, and p-space, no.
Just the problems the category.
Well, for instance, there's class of problem even harder than NP, I would say. Like a p-space complete is considered even harder than NP complete. Okay, so I probably wouldn't go that far. I mean, well, but what I'm saying is, by just knowing definition is not good enough. In general, it's about the fundamental thinking of what problem you consider is hard. And that's the difference. Okay, so I guess let's look at some problem that's very interesting and not so clear how to really apply greedy algorithm to that problem, but it has something to do with very important thinking process that will hopefully help you to design some good algorithms. And first, let me talk about the problem. And this problem, while in the abstract setting, probably is hard for you to comprehend, but let me try to explain a little bit. Let's assume you have a set U that contains n elements, what we call the ground set. And then you have this W, that's the collection of the subset of this ground set U, meaning what? For instance, if this U contains 5 elements, 1, 2, 3, 4, 5, and this W could be what? For instance, could be empty set, could be a set containing 1, 2, or maybe 2, 3, or 1, 3, 1, 5, etc. So that's a collection of the subset. And how many subsets can I have for ground set U? Ideally, I can have 2 to the power of n, right? And okay, so now let's think about how can I color this element so that what? So that the discrepancy on these subsets would be considered minimum, meaning that, for instance, if I have one element, 1, 2, 3, 4, 5, up to 100, I can always say 1 is the color red, 2 is green, and then red, green, etc. And by doing this color, basically I want to know for each subset, like how many reds and how many greens. I want them to be more or less balanced so that the maximum discrepancy will be small. Okay, so let me use this notation to denote the overall discrepancy for this whole collection of subset. Okay? Is that clear? Yeah.
Each element UI is mapped to 5.
Well, maybe let me give you one example about how to show the color in a graph. Sorry, how to just label this. Let's say I have 1, 2, 4, I have 5 elements. Okay, sorry about that. Need to change a little bit. And then I say this is the element. I will use 2 colors. This is 1 color, and then this is 1 color, and then this is 1 color. Okay, so this is basically the set. And this is my set U, 5 elements, okay? And W contains W1, which is, for instance, 1, 2, 3, 4. And then W2 is 2, 3, 5. And W3 is 1, 2, 3, 4, 5. Okay, these are the subset. These are subsets of U. Okay, and discrepancy is about what? Like how many elements labeled in this case orange, and how many in purple? Well, probably from here you can now see. So I will put a check here. These are marked in orange, and the rest are marked in purple. Okay, so by looking at this, I can count the discrepancy for W1 is what? The difference in these colors is what? Because 3 elements are colored in orange and 1 in purple, so this is what? 2. And then 2, 3, 5, 2, 3, 5, that's 1. 1, 2, 3, 4, 5, that's 1, right? Okay, so the maximum discrepancy for this whole set is 2. Clear? Okay, so if I gave you W2, W1, W3, if you color this way, then the discrepancy is 2. And the question is, for instance, if I gave you W1, W2, W3, you want to find a coloring scheme that can give you the minimum discrepancy. In this particular example, can I make it with discrepancy 1 instead of 2? Is it possible? Okay, so I make this 4 the same color as 3. So in this case, this is purple. And what will happen for the first case? Discrepancy is 0, right? And for the second case is what? 1, right? And for the last case is 1. Okay, so what Sayer proposed is a better coloring scheme compared with the initial coloring. Okay? So now, look at this optimization problem. What I want to do is to find a particular coloring scheme that can make this discrepancy minimal. Okay? So of course, this is just mathematical formalism that I try to build an instance matrix on the subset of W so that I can write this as a formal optimization problem. But you can see the key is what? To find a good coloring sequence on these n elements. But of course, if you say I can exhaustively enumerate how many different possible coloring schemes, each element can be colored by either red or green. So it's 2 to the power of n, right? And that's not efficient. Agree? If I do enumeration. So in any way, we can find efficient coloring scheme that guarantees to achieve the minimum discrepancy. And in the absence of any special assumption of this set system, I would say it's very difficult you may ask the question, what coloring scheme would provide close to the worst case minimal discrepancy? And in fact, this problem is not just for pure mathematical interest, because this discrepancy measure is highly important toward some real engineering applications, like a quasi-Monte Carlo method to generate some sampling points, or maybe experimental design where you want to have all these factors being more or less balanced in your designed experiments. And also here, efficiency is basically the key to beat any random sampling technique or random experiments that can not provide as good in performance as what we designed in this discrepancy system when you gave me the subset of this W. Okay, with that being said, so now can you invent some good algorithm that beat the exhaustive enumeration? Yes.
Well, you can graph a set Wi
Okay.
and randomly pick one and
Okay.
minimize its discrepancy.
Okay.
You should always be able to get either 0 or 1. If it's even, you should be able to get 0. If it's odd, you should get
Okay. Okay.
And then apply that system
To the next subset, and then keep doing that.
Keep doing that, yes.
Okay, so that's greedy for sure, but can you guarantee to achieve the minimum discrepancy? Okay. So now we have to think carefully, is there any way we can be greedy and still try to avoid exhaustive search and also guarantee to get too close to the minimum discrepancy? And that's hard, right? And in fact, if you look at this problem, I would say it's not NP complete. It's not even NP hard. I think when I presented at the group seminar, someone asked me, what class is this? And the answer is it's actually in complementary NP. And I just asked Lippy, I think that was not taught in computer science, so I don't know how should I explain. It's something like the problem is not as hard as NP hard problem, but still, we don't know if there ever exists an efficient way to solve the problem. Okay, so that's the level of difficulty you have to think about. Now, how can we be greedy in terms of coloring this? For instance, we cannot just say pick a particular subset and then do a balanced coloring on these elements. I hope later we won't have any problem. Okay, so in this case, you have to examine all the subsets, right? In order to what? In order to make sure that when you assign a color to a particular element, it will balance somehow among most of these subsets you're going to explore. So if you think about, this is not easy, right? If you really want to do some design, but then another nice thing you will see is that, in fact, if I don't do any design at all, things may not be terribly bad. Think about if I pick an element just randomly put a color without even worrying about this subset W, what will happen? Well, anything can happen, right? But what I'm trying to say is when N is large, and when you think about for large-scale problem, overall, if every element you just randomly assign a color, of course, in general, number of red and number of green elements are more or less balanced, right? Because each time, just I say, I independently and uniformly flip a coin and then just determine the color. Is that bad? Well, that's not really as bad as what you originally thought. In fact, you can say if this coloring scheme to a particular subset Wi is bad, if what? If you think about the discrepancy on this subset is greater than what? 2 Wi log 2m. What does that mean? Well, this 2m means like how many subsets you have. And then for this particular subset is bad, meaning what? Meaning most of the elements you labeled only in one color, so that description is large. And how large is considered very large. It's based on this scale, right? This is the right scale you are looking at. Why? Well, that's a little bit about the probability theory. If you think about Chernoff bound says that for a particular subset, if this coloring scheme is bad, then what? Then the probability that this will be bad is only smaller than 1 over m, meaning what? If for this particular subset Wi is bad, maybe for next subset it's good. If you have more subsets, this thing is not terribly bad. So what can we say? If the first coloring scheme fails, we should just keep trying. The probability of unsuccessful to make these discrepancies great smaller than this is actually on this order, 1 over m to k over 2. And what does this small o notation mean? Well, I think big O notation you already explained. And small o notation means what? It's asymptotically it's no larger than this order, meaning that it can grow what? For instance, it can grow m to k to the 1 over m to the power of k, but can not be slower than m to k over 2. Make sense? Yes?
So you can pick up small o as the best you can do?
Well, I'm saying that in the worst case, I have overwhelming probability that after doing this random coloring many times, I will succeed, provided they are truly random. And the discrepancy of the set system does not exceed this difference, meaning that if n elements, this is like the how many subsets you have. Ideally, in the extreme case, you can have what? 2 to the power of n possible subsets. So this log is on the order of n. So n squared is overall is n, right? Meaning that for a small piece of the 2 to the power of n subset, this shouldn't be a large number. And this order cannot be further improved without making any additional assumptions. Basically, that's the beauty of randomized algorithm. If you think about, if you want to design a deterministic way to find a coloring scheme, it's actually very hard. If you want to be greedy on a particular subset, it can be miserable. However, if you just do some random trials, you have overwhelming probability being successful. And of course, that's not the end of the story. Otherwise, we are not going to talk about the greedy algorithm. So random algorithm does provide you some insight. If you just randomly label the colors, it would be good. And now let's think about how can we make sure that we can go for greedy. If you think about, this is just an indicator function saying that for subset Wi, and my dirt I is just indicator, which means it's either I have a good coloring scheme or I have a bad coloring scheme. Okay? So overall, I want to count how many bad coloring schemes do I have for all the subsets. Okay? So now, let's consider coloring these elements without even going for backtracking. And the criterion that I'm going to use is to just find this, basically, the indicator function with respect to what? The posterior probability that I try to minimize this, basically, the indicator function, I want to minimize the expected by the coloring instances. Okay? Meaning that, for instance, if I have 100 elements, and then let's say if I have 1,000 subsets, and what I'm trying to do is, for instance, if you do just randomly assign colors to these 100 elements, then you have to try many times. But what I'm doing is slightly different. What I'm doing is, at each step, I just do the greedy calculation on the expectation, and this will only require me to compute the sum of those probabilities from actually a binomial distribution, right? Because originally you can say I have equal prior, and then based on observing a particular subset, then I have these probabilities saying that this basically is a good coloring scheme or bad coloring scheme, and I can minimize that. And by doing that, basically I just compare if I color this element to be red or green, which one has larger probability to make this smaller. Is that clear? And this is a deterministic procedure which requires the time complexity only on the order of n multiply m. When m is small, meaning that when the number of subsets is not 2 to the power of n, then this order is significantly smaller than what? Doing the exhaustive enumeration, which requires 2 to the power of n. So this is really a very nice algorithm. And that what it does is to be greedy somehow without going backward. But it counts the posterior probability of labeling this into a particular color being good or bad. Does this greedy algorithm really provide the desired discrepancy or not? So that's important mathematical question to ask. And in fact, it does, because it does provide the desired discrepancy like what we can hope for. If you think about, this is the expected bad coloring, number of bad coloring for the whole subset, for the collection of subsets. And that we want this to be smaller than 1 over square root of m, and that's basically the order for large n. And we can directly show that at each step, this expected value is this posterior mean is non-increasing compared with the prior, and thus, in fact, the number of bad assignments in the final stage is being what? Is being 0. Why? If this is non-decreasing, and at the very beginning, you have what? You have the expected to be bad coloring to be bounded by this. Then eventually, after seeing all the subsets, when you calculate this expected value, then you know that I cannot have bad coloring with this greedy step. So you can say this greedy algorithm is as good as the originally proposed the randomized algorithm, since the cost function has already incorporated all the necessary information that you need to see in the future by this very compact probability model. So what does that mean? It means we de-randomize an efficient randomized algorithm so that the complexity is significantly reduced. So now from this example, in effect, you already see like two types of algorithm. One is called the randomized algorithm, meaning that you use random source to do the coloring in order to solve a complicated combinatorial problem. And also you see another technique called the de-randomization, which reduces the requirement of generating random numbers, but still maintain the same performance. Okay, so I guess that's pretty much about combinatorial problem. Yeah.
In each step, you check the expected difference, the maximum of the.
Well, you check the expected bad coloring, like number of bad coloring. If for instance, if I assign this element to be red and green, which one will produce larger probability of bad coloring, number of bad coloring. And that can be computed based on updating each element. Basically, when you count each element, you have the prior probability they are equal likely to happen. And now you just count each column of all the collection of the subset. And then you will know.
Then why is the equation expected value given the U1 is V1?
Well, this you already colored. When it comes to the next stage, basically you colored U1 and then you move to U2, right? Once you colored U2, you don't change, and that's greedy, right? And then basically you just continue until you color the last element, and then you're done. Up from K, you move to until the very end, you get to N.
Sorry, I still don't get why it is straightforward to show this equation and why the left side of this encoding is defining this way.
You mean this part? Oh, this part. Well, this part, if you have not taken probability class, I would say maybe I cannot explain in a few words. If you don't see that straightforward, that means it takes time for me to explain. Okay, so I guess sorry about probably I shouldn't put the wording like that. It is straightforward. I think for those who are familiar with the probability language, it is straightforward to see that. But overall, this basically tells you an important technique to design greedy algorithm, which is greedy on top of some randomized algorithm. Well, I guess there's like a practical joke, like life is already full of discrepancy. Why do we care about this? So let's look at some real optimization problem. I mean, optimization in real space, not combinatorial anymore, but still it has some discrete nature in it. So let's think about how are you going to represent a function f based on a collection of different terms. For instance, this f could be, let's say, some time domain function. And then you say, I want to decompose that into what? Maybe a collection of sinusoids, right? And what do you do? Of course, you say, well, I do, like for harmonic analysis, I do Fourier series expansion, right? And that's one way of looking at this. And another way, you can say, well, now f is something I want to analyze, but I don't really know a good way to collect those basis functions. Meaning that when you do harmonic analysis, you already know you are looking into different harmonics, right? And sometimes I don't. Then what can I do? Well, I can say I can have a big dictionary that contains all possible bases or words. And then you say, OK, you gave me f, it's a sentence. I want to decompose that into the very compact representation of the phrases. Does that make sense? Well, I think maybe in those bioinformatics area, they have a huge collection of gene signals. And then you'll say, well, I have some microarray data that's the expression of some collection of genes, which I don't know, but I know it's come from a huge dictionary. And now I want to find out for this particular signal, basically what hidden signal, what hidden genes can best construct that using a linear combination. Is that clear? Well, in some extreme case, you can say if my dictionary contains orthonormal bases, meaning that like in harmonic analysis, then it's easy, right? You say, well, any signal, I do what? Decomposition. I project into each basis. I find what? The coefficient. And this idea can be similarly described by so-called basis pursuit, meaning what? You have original function f, and then you have a collection of dictionary, and then basically you project your signal to what? To each basis on your dictionary. If your dictionary contains redundant bases, doesn't really matter. You try to pick the best one based on the projection. And how do I evaluate which one is the best? Well, the greedy step means what? I choose one basis at a time. The first basis I'm going to choose basically just I project my signal to all possible basis function and then check the residue. Which projection direction is the best? The one with the minimum residue, right? So in that case, I can calculate basically the correlation between my signal and the basis and find the maximum correlation and then project my signal to that direction. And then what? Basically, I just repeat this procedure until what? Until I collect n terms. This is basically a greedy algorithm for sure. But would that work? Like I said, if you believe that you have a complete orthonormal basis, then this projection should work. Do you agree? Why? Because you know that the projection is basically good if you think about just three-dimensional space. Any point you project along x and y and z direction, they will not interfere with each other, right? That's like you have so-called orthonormal basis along x, y, z directions. But of course, this coordinate system is arbitrary. You can rotate this x, y, z arbitrarily. And they all form so-called orthonormal bases. But the problem is, let's say if my dictionary contains 6 bases, in three-dimensional space, they cannot be orthonormal for sure, right? And what? I can find what would be the best 3 bases to represent my f. If I only want to find the best 1 basis, what do I do? Still do the projection. But would that be good? For 1, I think greedy doesn't really matter, right? Greedy should work. For 2, would that work? We're not so sure about that, right? For instance, the best the direction on one direction could be bad, very bad on the other direction. And you could have directions where, like, you have 2 bases to span one function. Maybe one direction is very good, the other one is very bad. And then you have another plane where they are more or less balanced. But by doing greedy, you will miss that one significantly. Okay, so that's the situation when your dictionary contains so-called overcomplete, which means redundant bases. But you do want to find the best one. Okay, so now you can see we cannot be too greedy in that case. So, but we can still pursue along some greedy direction by slightly modify our basis pursuit algorithm. Now you can see that, okay, so I cannot be that greedy. But what? I do the projection. First direction probably is good. But later, maybe I need to adjust my projection because what? Because I cannot find other good directions. So what do? First, I do the projection. And then what? I span the basis to a linear space. And then compute the projection of my signal to this linear space, and then compute the residue, not to the projected gradient, but to this linear space spanned by my basis function. If my basis function is also normal, then this step is redundant because that's the correct projection anyway to compute the residual. But if they are not, if the bases are not also normal, then this step is important to make sure that I'm looking at the residual in the complement of my linear spanned space. Okay. I'm sorry? What is normal? Also normal means orthogonal and normalized basis function. Okay, for instance, if you think about the three-dimensional space, x, y, z, and then the basis is along x and y and z, that's one choice, right? They are orthogonal to each other. And then each element has a length 1, unit length 1. That's like also normal basis. Okay, so did that answer your question?
Yes.
Okay. Okay, good. So in this case, we need to construct this orthogonal projection based on the basis we already selected. And then we basically need to solve this simultaneous linear equation to compute the residual, and then go to another greedy step based on the residual calculated using this projection. Not projection based on basis, but based on the basis spanned linear subspace. I'm sorry?
How long you want to
Proceed until your approximation accuracy is good enough, or until you pick adequate number of bases. Okay, but still it's greedy, right? Because every time you pick a basis, you will not change your mind. There's no turning back. The difference is still about how the next basis will be picked, because that depends on the residual. And orthogonal matching pursuit is different from basis pursuit only in terms of computing the residual. Okay, so that's not really the only way to be greedy. If you think about greedy algorithm in picking the basis is just to search, right? And overall, you can say this problem is like what? I want to assemble the best team of 3 students. So what do? For instance, the greedy argument is that I first have to identify the best student, and then use that as like the stepping stone, and then say, for instance, if the best student is Mr. Liu, and then I will ask Mr. Liu, what do you think, who will be the best partner for you? And then he will tell me something, and then just proceed until I assemble the whole team. Is that optimal? Not necessarily. We don't know. It depends on the problem structure. But of course, we can still make this step not so greedy, meaning that, of course, you can go for pure greedy basis pursuit, or you can change the residual. But one way you can say, each step, basically, I try to approximate my function f based on this s and sn using some changing variable alpha and beta. One way I can say, well, I want to find the best value alpha and beta that minimize this whole function, meaning that this Sn is the best approximation to f, and this part is what? Another basis adding to it. Basically, by changing alpha and beta, I can recover basis pursuit and orthogonal matching pursuit as special cases. But putting more value on alpha, for instance, alpha equals to 1, what will happen? It's more important that this existing approximation to f should be good, right? And when you put beta equals to 1, what will happen? Basically, you try to count not the approximate, you use the approximate signal to the original signal based on the selected basis, and then you choose another one, and then you use them all together. Of course, these coefficients could be adjusted somehow so that it doesn't really matter what value it takes in order to approximate the signal. But overall, still, it's a greedy step. Because this type of algorithm, in general, is called the greedy pursuit. Well, of course, the pure greedy is the most efficient algorithm because every step is greedy. Orthogonal matching pursuit requires what? Some solving simultaneous linear equations by what? Spanning the linear space in order to compute the residual. And general greedy pursuit requires you to solve some kind of linear least squares problem, which in this case is solvable, but still additional computation is required. Okay?
Performance-wise, which one?
Well, performance-wise, I would say, of course, if you can design better for alpha and beta, of course, that can be better than greedy pursuit, but then orthogonal matching pursuit or all basis pursuit, because they are all special cases. At least you can change this alpha and beta value to reproduce whatever performance orthogonal matching pursuit or greedy pursuit can achieve. Okay, and then would that work, right? That's important. The key question is, does the greedy pursuit lead to the best n-term approximation for this function f? Well, and that's very important. And that's basically related to my research area, which basically has everything to do with how you form your dictionary. We know that in the extreme case, if the dictionary is not redundant, if there are also normal bases, this works, right? Greedy method works, right? And then we can relax a little bit. We say, okay, so in general, if they are not orthogonal to each other, but they are what? At least they are not very highly correlated, then what? Then probably it will work. So we say if the largest correlation among any pair of bases is below some threshold, then that threshold is what we call the incoherence of this dictionary. Okay, and if the incoherence of this dictionary is below certain threshold, which I will try to explain in details later, then this greedy method guarantees you to find the best n-term approximation. Okay, and in fact, that's important because, for instance, if you think about this f, for instance, this function, if that's some function which can be approximated by a few bases in your dictionary, then one would expect that you can actually sketch this signal with much fewer measurements than its natural dimension. Which means, for instance, if you think about an image in the raw data representation is you have each pixel value, right? And then you believe that in another representation domain, you can reduce this significantly. Why? Because the picture does contain some regularity in it, right? Meaning that when you cut it into small patches, when you do this zigzag rearrangement, when you do discrete cosine transform or wavelet transform, in that domain, there are only a few terms with large magnitude and other terms with very small magnitude, so that you can reduce the dimension significantly. Similarly, if you say I have a harmonic signal, then in the time domain, you'll see a continuous waveform, right? But in the frequency domain, you only see what? A few harmonics, right? So that's why, for instance, you can, in the frequency band representation, it's quite efficient. Similarly, for instance, for voice signal, you can say it has limited frequency band, right? So it has much compact way to represent in frequency domain than in time domain for the speech. Then, of course, you can do some data compression based on this kind of knowledge. And same thing for very generic signal f, which has a redundant, which can be compactly represented by some basis in certain dictionary D. So if that's the case, of course, one natural question to ask is, how can we make a very sketchy measurement so that we don't need this high dimensional raw data? Meaning that, for instance, if you have a camera, you don't need to get to this pixel value representation of the image. You say, I just do some sketchy combination of this directly so that basically a sketchy signal Y contains all the information you can see for this pixel value image. Okay? Well, okay, you say, wow, there are many different image compression algorithms like JPEG 2000 or maybe some other things can do this. But that's after you get to this pixel value representation, and then you do the compression to save it to your computer or maybe some other storage device, right? Is it possible that the camera or maybe a small wireless sensor can do this sensing directly without getting into that? And that's the question. People call that compressive sensing or compressed sensing, meaning that the sensory device should be designed that has inherent compression mechanism when this signal has sparse representation. And one way to look at this, you can say this phi is some linear mapping for this sparse representation, sparse signal f to some representation y. Meaning what? This f may only contain very few non-zero elements. Let's say the remaining elements are all 0. So what can I do? I can try to map this to some function y so that when I have y, eventually, when I know this mapping, I can pinpoint to what? Where are those non-zeros and what are the magnitudes? Okay? And the question is, how can I do that? Well, one way you can say I try to pursue for the sparsest solution. I say, given my observation y, I know this phi, so I should maintain y equals to phi f. And then what f? There are many f satisfy this equation because what? In general, y has very small dimension and f has very large dimension. So there are many f satisfy this, and I want to find what? The sparsest vector f, meaning that the f vector with the fewest entries that which are non-zero and the remaining are 0, and then I want that to be my solution. I'm sorry? That means the L0 norm, meaning that the number of non-zero elements in this vector f. Yeah. And in fact, it's not really a well-defined norm in Hilbert space, but still it's a convenient notation. You can, for instance, you can say it's LP and let P equals to 0, which will basically count the number of zeros. Yeah, because it's in the extreme case. But this problem is proved to be NP hard. So we don't want to try this one. Instead, we try what? A relaxed version. We say instead of counting number of zeros, we count what? Well, we count the total magnitude of this f, which is L1 norm. And you may say, would that work? And if, in fact, this relaxed version works most of the time. Whenever you solve this, instead of solving that, you solve this, you get the equivalent solution, provided this f is sparse enough. And that's very amazing, in fact, because you have a difficult optimization problem, which is NP hard, but we see that in some cases, it's equivalent to some problem which is definitely solvable. And that's really nice. And not only that, in many engineering applications, you don't expect this y equals to phi f to be exactly true because what? There are some noise. So you have to consider some noisy setting. In that case, you say, I want to find the solution f, which has the fewest entries of non-zero elements, and such that y minus phi f, this is like the Euclidean distance for this vector norm. And that's below some noise level, because this considers the residual between your phi f and the y. It's like how well you can approximate the measurement. And this problem can be solved by what? This is constraint optimization. And this part can be converted into linear objective function, and this part can be converted into a quadratic constraint. So overall it's what? A quadratic program. And it can be solved by some standard package called LaSalle, which is developed by some statisticians from Stanford University. And that can be solved efficiently. Instead of doing this, another nice idea proposed by Emil Candice from Caltech is using this so-called Danzig selector in memory of this George Danzig who invented linear program. And basically, what he proposed is not control the residual, but control what? The L infinity norm, which is what? The maximum value of this element, right? And what's this? This is nothing but the gradient direction of what? Y minus VF L2 norm, right? Meaning that if the gradient eventually is 0, then what? The maximum element should be small. And that's a very nice way to pursue for sparsity, where this part, in effect, can be converted into what? Linear program. So remember, from the first class, we see that the optimization problem can be formulated toward what you feel comfortable, right? For instance, if you can formulate it as a linear program, then don't formulate it as a quadratic program, or maybe convex program in general. If you can formulate it as a convex program, don't formulate it as a generic, nonlinear, non-convex program. If you know some specific technique that's applicable to this problem, then of course it's nice. And this can basically, Candice showed that this method can recover the sparse locations of F, while when you have this measurement map, this well-designed phi matrix satisfies certain incoherence property, which is what I just mentioned, that your dictionary need to have the basis. They are not really orthogonal, but you try to make any two pair of bases as less correlated as possible. Okay, so with that in mind, then basically we can also ask the question, now for this type of problem, can we apply greedy algorithm? And the answer is yes, of course. And usually greedy is even fast, more efficient than this. But of course, a relevant question is, can you still guarantee to get to close to optimal solution when you apply greedy algorithm, right? And that's the next level question. And that's very hard. And I think this is the most challenging part I try to explain to you. In a sense, this depends purely on geometry, nothing else. If you think about the redundant bases are just a framework to represent your signal, and there are different ways to represent. And in order to make sure that you have a unique representation for sparse signal, what do you need? Sparse means what? You can arrange your high-dimensional space into low-dimensional subspace in some unique way. Okay? And in order to understand the geometry, we need to think about, for instance, any linear mapping of this function f in high-dimensional space into a lower-dimensional subspace. What will happen about the distance? Any 2 points, if they are originally far away from each other, after the low-dimensional embedding, you want it to be still far away. If they're close, you need it to be close. And the distortion is measured by Euclidean distance. And if you can preserve basically the distance from the high-dimensional space to the low-dimensional space with respect to some epsilon level, then you're done. And the point is that only certain function you can achieve that. And some function, basically in order for your approximation to be close to this function, the mapping has to satisfy so-called restricted asymmetry property, some people call RIP condition. And this condition, if it is satisfied, then there exists an efficient way to sketch this so-called k-sparse signal f, meaning that if original dimension of this signal f is n, and it only has k non-zero entries into this F, then what we need for this dimension, for this observation vector dimension y is only at the order of k log n. Meaning that, for instance, if this n is 10 million and k is 3, then basically this scales in the log of your original dimension. Meaning that originally, if you think about the 10 million pixels, if in fact, if it's representing only very sparse, meaningful image, then basically you can downscale by log. Is that surprising? Well, I hope so. And in this particular setting, you can see that the efficiency part is important. Basically, you say, wow, yes, you can recover that. However, this phi, for instance, is it unique? I say no. In fact, you can use any well-designed random matrix where each element could be drawn just independently from some Gaussian distribution, and that's good enough to achieve this mapping. And in fact, there's a well-known, not well-known, but I think this was proposed in 1984, but only very recent years people pay a lot of attention to that. This Johnson-Lindenstrauss lemma says that for every set U of m points in some Hilbert space, n-dimensional Hilbert space, there exists a locally Lipschitz mapping such that you can reduce the dimension from capital N to N, where basically N is on this order, depending on the number of data points you have, and also depends on how much distortion is tolerable. I'm sorry? Well, I believe for Hilbert space it's true, but for general space I don't know. Because this, I think very recently this Lindenstrauss wrote a note saying that Hilbert space probably is the best space you can do geometric embedding. Meaning that other space probably is not of a lot of engineering concern that we want to explore, but basically that's what I know.
So what is Hilbert space?
Well, what is a Hilbert space? Repeat, please.
Hilbert space is an inner product space. There should be an well-defined inner product in that space, and with respect to, so every inner product will give rise to, with respect to that inner product, the space should be complete. It's a complete inner product space.
Well, a space is where you can describe the data points, right? And in general, if you want to say how close this point to that point, you need to assign some distance, right? And then that's where to start talking about abstract space.
Inner product.
Yeah.
So suppose you have a space in which you can define an inner product. And if you have an inner product space, then using that inner product, you can define a certain norm. That is the distance between two elements.
Yeah.
Using that inner product. And with respect to that norm, the space should be complete. Complete means every Cauchy sequence, it is in terms of Cauchy sequences.
Yeah. Well, I think this is like, how should I say, the formal way to describe this should require functional analysis. Anyone heard about functional analysis? I mean, I'm asking other engineering students. No, not at all. Okay, and that's hard. But in engineering term, basically, if you talk about a space, it's just a collection of data points, right? Right? In general, this three-dimensional space, how do we know this is a space in some abstraction? Need to say data points, right? And then also we need to what? Measure the distance, right? And that's like how we create abstract space, where we care about the distance. And also we care about the sequence of distance that we can talk about converge, limit, things that we can say this is close to that in the limit, okay? And sometimes we need to have better representation for this space, meaning that, for instance, can we use basis? And that's why we need to have some kind of inner product and the representation. And sometimes we want to say the space is complete because what? Every single point, we need to find a good representation. And also, if you consider any converging sequence, we need to find it will get to a valid point in this space. Okay, so basically, then the mathematicians will come say, okay, these are just intuitive terms. And if you only rely on that, we cannot make it formal. there are some bizarre behavior. We have to define this using axioms. And that's where, for instance, Libby comes in, saying, OK, so we have to define Cauchy sequence, converge, and continuity, and Banach space is like metric space with distance. And Hilbert space is what? With inner product, and also it's complete in terms of you can rarely find any point with a representation from some basis, right? And of course, the number of bases can be countably many if you want to have some very abstract space. And sometimes can be even uncountably many if you consider very abstract functional space. But anyway, that's beyond the scope of this talk, so I'm going to stop here. And saying that the proof of Johnson-Linden-Strauss lemma, in fact, is not that hard. If you know probability and random processes, probably you can prove that. But the problem is you don't understand the implication of what it means. In fact, this is the key that link to compressed sensing concept, where there's a hope that using greedy algorithm, we can de-randomize basically this kind of grid, like combinatorial discrepancy type of method, some algorithm that reduce the combinatorial discrepancy, and also by the same token, we can de-randomize this compressed sensing matrix phi, and then try to apply greedy pursuit. So basically, to give you some flavor of what I'm interested, one is that, for instance, is there any way we can perform this Johnson-Linden-Strauss transform, meaning that map a high-dimensional signal to large-dimensional space with low complexity, and then apply basically one particular mapping to all possible sparse signals so that we can recover it efficiently. And that's the whole goal, is to, for instance, if you have high-dimensional data with some structure, there's an efficient way to work in the low-dimensional space. And then once we process the data, we can still recover the sparse signal in the high-dimensional space. OK, so sure.
Greedy algorithm, you need a step by step.
Yeah.
In this case, how you do it?
Well, you pick one basis at a time, right? And for instance, if you say, I want to know what are those non-zero elements, one greedy approach is say, well, I try to find the first entry that's non-zero, which can approximate the signal best, right? So it boils down to signal approximation that I introduced before. So you can apply, for instance, greedy pursuit, which is pure greedy. Instead of doing quadratic programming or linear programming, you can pursue for greedy approach, which is more efficient, but you have some price to pay, which I will not talk too much. So maybe why don't we take another short break, and then I will ask you for another 25 minutes to wrap this thing up, so that I hope you can get some flavor of how the greedy approach can be applied to some interesting engineering applications. So maybe 5 minutes break, and then we wrap it up.
It's too hard.
I agree to fully understand this. It is still hard.
Vaguely understand.
Yeah, so that's why I think there's a need for discussion and for recitation. That's
also very hard on whoever's writing the notes.
Yeah.
That's a very hard job.
Well, at least I hope it's a rewarding one.
But it's very hard.
Very.
Very hard.
I will just, let's say, watch the video and write down whatever you said. So.
Well, that's not the best way to practice. In fact, for instance, when I heard the term like this global convergence, I did my homework and looked into at least 3 textbooks and Wikipedia. I couldn't find a satisfactory solution. And then I said, maybe I'm wrong. And then I looked into operations research and consulted with a colleague of mine. I still couldn't find satisfactory answer. So
that's a lot of work just for one term.
Yeah, well,
4 of them on a single slide for us, you know?
Yeah, but in this case, I'm saying that if the understanding will lead to somewhere, for instance, if I say, well, because this global convergence concept is important to assess optimization algorithm, then I need to know. And that's why it drives me to really get to that. And right now, I still don't have satisfactory answer to that. I just say, well, the original definition doesn't look appealing to me, and I want to know why. Is there any way to refine that?
But if you were in our positions,
Yeah.
you're learning about like optimization
As a whole, yeah.
as like an introductory course, you know.
Yeah, I know.
So global convergence is not at all my primary concern. Like if I saw that term, I would just ignore it for the next couple of years.
Well, yeah, I would say global convergence.
Well, no, I'm not saying
To,
global
yeah,
convergence in it
yeah,
as a specific.
as a term,
Right.
to me, is meaningless unless I know how to apply that to
Right,
assess
but-
the optimization algorithm.
But even if I knew how to apply it,
Yeah.
we're still learning optimization itself.
Yeah.
So there's like 4 fundamental layers below that explanation that we need first.
Well,
yeah.
I personally disagree. I feel, for instance, if it's, of course, this is an introductory course for sure. But what I'm saying is, if you don't see the cutting edge flavor, then basically you only get to know, well, I know Lagrange multiplier. I know this. I can solve some problem.
Seeing this and understanding it. Are
Yeah,
very
it's
different.
I know. But what I'm saying is,
Long shot in the recitation notes is to understand it.
well, I hope.
That's hard.
Yeah, I know. So what I'm saying is, even if you, for instance, you say I wrote this, I don't understand 95% of that. Still, it's a good learning practice, because later, when you maybe after a few years, when you look back, you have better understanding. That's already my job is at least for you to at least have some memory on what you learned.
Okay.
Because, for instance, otherwise you will never even realize for greedy algorithm, there are so many depths, so many layers on top of that.
Yeah.
You'll say, well, greedy algorithm, that's easy because for minimal spanning tree, that's optimal. And for other things, usually there's no hope, period, right? And that's the end of the story. Maybe even after so many years, still, yeah, that's your view of greedy algorithm. And
Focus is we understand the gradient and where you can apply it, how apply it.
you cannot, that's what I'm trying to say. But at least I will tell you there are some interesting directions to look at. Because if you say, I can understand, no, I think even after so many years of research effort that I've made, I still cannot say I understand the whole thing. But at least I hope you think this is interesting, even though it's hard, but still you understand why it's hard. For instance, not just, not just say, okay, that's hard, that's NP complete. And sometimes you say, what does that mean?
You're only aiming for 5% understanding. Keep that in mind.
I only got less
Well,
than
well, that's just an analogy. In fact, you probably can gain more.
I mean, it's
Yeah,
the
as-
fastest course you have ever had. You speak is fast.
Oh,
Fastest in
yeah, all the lectures.
Looks like you are rushing your car.
This is your research area, so you have
You
no
are very
fluency
good
here.
familiar with that, so you can go fast speed.
Okay, yeah, I can slow down, at least for the next 20 minutes.
Yeah.
And
These really in-depth topics, they are good to see. They do pique interest, but they are very hard.
okay,
Like even seeing them and keeping track of things is hard sometimes. But I don't know. I feel like if you could come up with one distilled, not a formulation, because even the formulation sometimes is hard. But if you could come up with one clean example
okay,
that just shows where the difficulty is. Sometimes they say that picture is worth 1,000 words. You know?
yeah,
That might be useful for us to see the complexity, not to really understand it.
yeah. For instance, this coloring, I would say,
That was
yeah,
a good example.
yeah, that's
Like that made a lot of sense to me.
Yes.
that one. I think takes time to fully figure it out.
Right, but
Yeah.
just showing us the problem also showed us the complexity behind it.
Yeah, that's where, for instance, the recitation probably will be helpful, because that's what I hope, because that makes some sense, right?
Right.
For the following questions, you can for some numerical.
Oh, you mean?
Sketches. You put sketches.
Oh, you mean this?
Yeah, let us understand the problem.
Yeah, this, for instance, I would say you need to attend tomorrow's seminar. Right, for this, yes.
You know, there is L0 norm, L1 norm, L infinity norm, right? What are these norms?
Well, that's not hard because, for instance, L0, simply put, is just a vector. You count how many non-zeros in it. L1 is just take the absolute value and take the sum. Yeah. Yeah, and then L infinity take the maximum value. And L2 is the Euclidean distance. In fact, this you can also interpret it in the limit case because you can always say LP, right? Which is just each element take raised to the power of P, and then take the sum and take the square root, well, the P's root, yeah. And then when you let P approach to 0,
you get this L0.
Yeah, you get this definition, which is not a legitimate norm, but still it's a well-defined measure. Okay, so I think Rustin complained that this is probably the fastest pace in all my lectures, and also probably the most abstract one. Takes a lot of effort to digest. And of course, what's the purpose of this in an introductory level of optimization? So maybe let me try to convey the message that if you don't see some cutting-edge optimization techniques relevant to the engineering applications, then probably you won't realize some interesting research driving force toward that end. So I would say at least some certain exposure would be adequate for you to at least understand about the research problem we are looking at. So I always feel that, for instance, as a graduate student, you can, of course, find your own research area that you show a lot of interest and also maybe dedicate a certain amount of time and get into some level of depth in order to understand the problem better. On the other hand, I would say greedy algorithm on the surface is very easy to understand. And also sometimes relatively easy to construct the algorithm, but very difficult to prove anything that it works. So in general, I will say a global objective function can be decomposed into finite or countably many stages that you can optimize. And this looks very similar to dynamic programming setup, right? But there should exist some efficient algorithm to solve the sub-problem at each stage. And you can say the greedy algorithm acts like some coordinate descent or successive approximation, but relies only on decisions being made so far. Meaning that if I make my decision, there's no turning back. On the other hand, other algorithms, usually you have to change your mind back and forth. That's less efficient. So greedy is efficient. Unfortunately, for a given problem, there's no systematic procedure to answer whether a greedy algorithm will find the optimal solution in polynomial time. By asking such a question, in fact, the answer lies in so-called P-space complete category, which in layman's term is, you can say, one level harder than NP complete. Okay? Because NP complete is just about the time, computational time, has nothing to do with the restriction on the computational resource. And then P-space complete is like one level harder. So there's, in general, no hope that there's a course just say how to design an algorithm that check whether a particular optimization problem has an efficient greedy solution. Near optimal greedy solution. Because greedy usually is efficient, but we don't know whether it's near optimal or maybe even the optimal one. And this works for submodular function minimization, like what I mentioned before in another very challenging lecture, I would say. But still, it's not very difficult to comprehend that at any time of greedy iteration, in order to maintain optimality, you need to keep relative density of the good events reachable from the current state, and usually to be bounded from below. As long as these densities, or they are good enough approximations, can be computed efficiently, then the method in general will reach a good event in polynomial time. Okay, so what does that mean? Still say, I have no clue. Okay, so let's look at another example. If you think about a skier just go from the top and then downhill to do the skiing. Okay, let's say there are different forks, different intersections the skier can choose which one to go. Okay, of course, the overall objective is to, for instance, going from here, there's one branch, either A or B, and then another branch, and then maybe another branch along the intermediate steps. Okay, so let's say the skier has to determine which direction is the steepest descent from the top to the bottom. Okay, so what decision he needs to make is at each intersection which way to go, right? And can you design an algorithm that's greedy? How do you design that? Okay, but would that guarantee you optimal? No. Okay, so any direction that's greedy and still can guarantee you that's optimal on average? On average, meaning that from top to bottom, this is really the steepest descent direction. You can put some value. For instance, this is like the slope is 0.8, this is 0.7, and then maybe this is 0.2, this is 0.3, so on and so forth. Okay, so like what Rustin said, if at any particular fork you just follow the steepest one, that's greedy for sure, but there's no guarantee. On average, you will be the best, right? So what do? You'll say, well, I can slightly modify my greedy step by what? If there's a branch, I need to pick one. Which one? I need to know what? On average, this slope is deeper than that one or not, right? And then I will pick that. And then you'll say, how can I get on average the slope information? Well, I can always go what? From bottom up, right? Meaning that from this level, I know, right, which one is larger. For instance, if you say this is 0.1, this is 0.4, then I know for this node, on average, my slope is some value, right? For instance, I say this is like what? 0.25, right? And then similarly, for this level of node, I will know the average. And then based on top of that, I can compute. And then what? When this skier needs to make a decision at a particular level, in the first level, I already know what? Which way to choose. Once each node reports its level to its parent, and then basically you just propagate the average to your parent. After you compute the average, you propagate that to your parent node, and then the skier can choose which way to go using greedy algorithm. Yes?
Instead of average, can we modify it and take the maximum min of the path?
Yeah, you can. And sometimes, and do you think that's optimal with respect to average descent? I would say probably no. That you need to mathematically show the procedure works.
If you actually take the steepest path starting from the bottom,
Okay.
if you keep track of it, go up, doesn't that give you the optimal steepest drop?
Not necessarily, because certain branch, maybe you have flat portion and then a very steep one. And then basically, even if you start from bottom up, still there's no, unless you do some kind of dynamic programming from below, but which is not really the case that I'm trying to argue in this scenario. Well, with this example, I hope to convey an important message about the greedy algorithm. You can say that a steep trail might be followed by a flat portion. So in general, at each fork, the skier can choose the trail whose average slope over all descents from that trail is the maximum. And that's a greedy step, right? There's no turning back. However, this decision is non-local. In order to make sure that eventually you get to the steepest descent, on average, at each fork, your decision is non-local. And if you look at this combinatorial discrepancy problem, you will see very similar pattern. But of course, that will take Mr. Gang Liu a lot of serious effort to get to that. And I also hope that other students can contribute in terms of discussion or better understanding on this subject so that you basically can gain something. And let me just try to summarize what we've seen from those examples. In Markov decision process, basically one alternates between value iteration and policy iteration to avoid exhaustively search over the whole state space. And in finding those low discrepancy sequences, we start with a randomized algorithm and basically shows that random scheme is efficient and not so bad on average. And then we construct an objective function of greedy type via so-called de-randomization. And these are important tools, actually very popular in algorithm design in computer science, which probably shouldn't belong to an optimization class, but I want you to be aware of that. And of course, in this university, we don't offer algorithm design class at the graduate level that appreciate randomization or de-randomization algorithms. Is that right? I think it may be in other universities. I believe so. Yeah. And the key ingredient in this, of course, is to understand how the randomized technique works in some particular setting. And for sparse signal recovery, we basically exploit the so-called mutual incoherence property of the redundant dictionary. And that would also help us to construct a so-called measurement matrix that can achieve compressive sensing, like sketch the sparse signal, so that we can recover with high fidelity. The key ingredient in all these examples is that we treat each greedy step as some coordinate descent and show that basically we can do successive approximation like a fixed point algorithm, meaning that we show those good events that lead to optimal solution will never be away from our greedy approximation. And that's basically the engineering term to interpret some abstract mathematical thinking. Okay, so now maybe let me just say greedy is just one small piece of the optimization problem, well, optimization technique for engineering problems. And there are many others. And I would say most important thing you may want to be aware of is, of course, the branch and bound. And that can be combined with greedy heuristic, especially when you design some good optimization algorithm. Usually it's a combination of these tools. Like branch and bound, in general, you cannot ensure the best decision made on the current stage will be useful for the future action. Then you need to do some efficient test on the optimality or non-optimality in order to basically throw away some unnecessary feasible sets being searched in the later stage. Among those branched search directions, if the lower bound for some tree node is greater than the upper bound for other tree node, then basically you can stop for certain branches. And keep good nodes in the greedy search is always the key to control the complexity. So in conclusion, I would say a greedy method in general provides efficient solutions to very challenging optimization problems. And sometimes it's very easy to find a greedy algorithm, but it's hard to justify that it works. The most challenging part is that the best decision made at each stage is in effect non-local. However, there's still a hope that we can recover near optimal solution with high probability, even though we cannot show this is true. In some problems, there's no way we can rigorously say greedy method can give you the optimal solution, but there are some ways to justify it can give you near optimal solutions. So maybe let me just try to recap basically what we already talked about in optimization, so that during the spring break, if you still have some time to explore the lecture notes and the textbook, then it would be nice at least to go over these keywords. One is that for continuous objective function, basically we follow gradient descent as an important numerical algorithm. And also we have so-called stochastic version of the gradient descent for stochastic optimization. We talked about constraint optimization in terms of Lagrangian relaxation, which can also work on mixed integer and linear program, or maybe discrete and continuous combined optimization problem. We talked about the duality concept and how to convert the primal problem to the dual problem, which is considered not so easy, but I hope that with maybe one or two examples, you can see the connection for that. And we talked about successive approximation in some very narrow setting, where basically you decompose a big problem into small stages and try to solve that successively. We talked about the branch and bound technique to relax the integral discrete constraint so that we can find upper lower bound for some branch nodes, and then we try to find a good heuristic to reduce the complexity of the branch or bound. And I gave one example on the combinatorial discrepancy, which contains both randomized and de-randomization algorithm. And also, we have not talked a lot about the geometry embedding and combinatorics, but basically I just gave you one example related to my own research interest, which is compressed sensing using basically low-dimensional measurement to represent a high-dimensional sparse signal and try to recover that to the best extent. We talked about a few greedy approaches to solve the problem, and also linear programming as well as quadratic programming as optimization formulation to solve this sparse recovery problem. I think maybe Lipi's research is relevant toward this. So that's also one important engineering application. Okay, so overall, I would say there are many non-greedy methods available in optimization literature. I can only give you some big hints on this. One is called the divide and conquer, which usually whenever you learn algorithm design, that's like the stepping stone you have to get through. You need to know what problem can be arranged so that you can do divide and conquer. And also probabilistic or randomized algorithm, which is considered usually advanced graduate level in algorithm study. And heuristic methods, which I think usually can be covered in operations research or optimization introduction level, which doesn't guarantee you anything, but sometimes if it works, then people like that. This includes simulated annealing, taboo search, genetic algorithm, and so on and so forth. And also the last part, I think is mainly in the recent years, people pay a lot of attention because what? Because of the large-scale engineering domain, like talking about the internet, like how to identify potential like malicious attack in large-scale network, how to understand design of the integrated circuit which contains billions of transistors, how to do reverse engineering for some very complex system. We need to explore some graphical model and also find a good inference algorithm over some graph with structure, for instance, by finding the minimum cut or maximum flow of certain graph, or maybe do the message parsing or network coding to effectively improve communications. And these are all relevant engineer applications where optimization plays an important role. So I think that's really a very compact lecture for tonight. I just hope that some of you may be interested in applying certain technique toward your term project, that I hope. But in the long run, I also hope that some of you may, when you have some research problem that you think it's challenging, you may take this as a particular resource that you try to find good references, where I hope Mr. Gang Liu will also try to provide helpful hints on the recitation notes, where, of course, other students are more than welcome to help him complete this mission. And of course, at the very end, we should give Mr. Gang Liu a big applause for taking the challenge, of working on these recitation notes. And that's a small trophy that for him. And okay. Okay, so with that being said, I guess that's pretty much for what I want to cover on greedy algorithm. And of course, have a nice spring break, but don't forget we have the computer assignment due. Well, and of course, if you want, you can submit a little bit late, but don't be too late, because we do have other subsequent assignment on Blackboard. I think after spring break, we have another homework assignment that you need to read the textbook and understand a little bit better about duality theory in order to work on that one. Okay, so again, have a good spring break. But if you do have some questions, feel free to use the class Blackboard discussion forum. I do hope that some of you may want to post your questions there. It's very convenient for me to respond to that as well. Thank you.